So after introduction, the first big topic is Bayesian inference for proportion. We actually saw like an example of this in class last time when we were trying to come up with a prior together about the all-nighters percentage of master's students from last year. So that's making an inference about proportion. Okay, so proportion is a random variable in this case between 0 and 1. And then we have particular data model that we're going to put on this, because last time we also see that if you're trying to make inference about the proportion, the observation that we get from the class is a binomial experiment. Okay? And then now we're going to learn more about how to come up with prior distribution for proportion. Last time we were doing this discrete prior. You remember, like I asked everybody's opinion, and there were like 23 students in total, so we can come up with a discrete prior that the proportion P can take 0.1 through 1.0, which has 11 options, right? So the process of asking you for your opinion, then come up with this list of probabilities that's coming up together to define the prior probability. So in this chapter, or this unit, we're going to learn again, just refresh a little bit more about how to come up with that discrete prior distribution, and then we're going to move to the continuous distribution for the prior as well, and then how to make inference about it. So I'm going to cover today the example and then the Bayesian inference with discrete priors. This is just hypothetically, I mean, Talk Express does exist, but this is just an example of thinking about proportion. So this is a popular Japanese restaurant on Lagrange Avenue, about 10 to 15 minutes walk from Vassar campus. So suppose the restaurant owner wants to improve the business even more, especially for dinner. And what the owner does is he plans to conduct a survey by asking their customers, what is your favorite day to eat out for dinner? Okay? And let's suppose that the owner wants to find out how popular is the choice of Friday. So this is a hypothetical situation that the survey goes out to a certain number of customers, and then each customer can only indicate one day, okay, out of the 7. So in that case, how popular the choices of Friday will be, we're looking at the proportion P of people choosing Friday out of all of the possible days. Okay, so this is a proportion of percentage, and then we're trying to, through this survey, making inference about, in general, what this P should be. So we covered last time a little bit about 3 general steps of Bayesian inference, if you remember. The first one is, well, before collecting any data, we should express our opinion about what the values of the proportion P should be before we take any sample, right? So that's what we say, that this will be a prior. And then step 2 will be, well, we have the prior now, and then we're going to take a survey in this case. That's the sample that we have, and then we're going to record the observed proportion. And for this particular setup, we define this step as the data/likelihood. I'm going to talk a little bit more about the likelihood, why we say that, but really it's related to that. You take the sample and then you get the data, you collect the data. Step 3 is you use Bayes' rule to sharpen and update the previous opinion about this unknown P, given the information that you have. Okay? So in the past, we've been writing the hypothesis, and then data, and then we go to the posterior, given the data. Okay, so now we are trying to formalize these 3 steps for this proportion case, and in particular, now the P hypothesis will become a prior distribution for P itself. Okay, and then here this will become the posterior distribution for P. The process is still the same, but then we have to be careful about each step, how to make it correct to do the accurate inference. So we're going to start with discrete priors, meaning that we will, first of all, in step 1, list a finite number of possible values for the proportion P. So again, it's a proportion, so it's between 0 and 1. And we're going to simplify a little bit just to list a finite number of the possible values. And then don't forget that in addition to the list of possible numbers, you also need to assign probability. Okay? And then the list of probabilities should follow the 3 axioms of probability. And that, the whole thing, completes the prior specification. Step 2 is the data likelihood part. And we covered it a little bit last time, but also this time we're going to cover more and review a little bit about the binomial distribution, binomial experiment to make sure that we understand why we can use the binomial distribution for the data. And lastly, for step 3, on the posterior, we're going to use Bayes' rule. And remember the Bayes' rule, we have the discrete case, which is using summation for the marginal in the denominator, or the continuous case using integration for the marginal. But because we're working with discrete prior in this case, so we're going to see how to use the summation for getting the marginal probability of the data. And then we're going to use that to sharpen and update the probability of each specified value for P. And that's the whole process. Okay, so keep in mind, this is the process. So we're going to see it one by one. So prior distribution. This is, again, percentage of customers' choice on Friday. Okay? And keep in mind that each customer can only pick one of them. So P should be from 0 to 1. And it's also keep in mind that it's before giving out the survey. We typically try to come up with prior before seeing any data. You don't want this two to interact. So to consider how to come up with a discrete prior, you can first of all list the possible values of P and then come up with probability associated with each P. So just for illustration purpose, I'm gonna assume that for now we can have 6 different values, 6 possible values for P. And it's 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, okay? And this is, well, mostly because it's asking, I mean, Friday is the beginning of the weekend, so it might be like higher than usual, so I wouldn't go like as low as 0.1, right? Because there's 7 days in total, so average every day has 1 over 7, which is a little bit over 10% probability being the choice. And because it's Friday is the beginning of the weekend, it's probably going to be larger, but it wouldn't be like as close as to 1, but it's possible to be large. Okay, so you can come up with different sets of possible values, but for illustration purpose, let's start with the 6. And it's discrete because there are only 6 possible values. Okay? So in addition to decide the possible values for B, we should also assign probability for it. Suppose the total experience owner believes that some values are more likely than the others among the 6 values here, and in particular is given this owner's prior. So remember last time or 2 times ago, I was saying that we always use pi to represent the prior distribution. Okay? So and we use the subscript here owner just to represent it's the owner's prior, and then the random variable here is P, is the parameter, and then according to the 6 different values here, we're assuming that the middle 2, 0.5 and 0.6, are twice as likely as the remaining 4. Okay, and then they add up to 1. Right? So really quick here for you all, is this prior distribution reasonable? Meaning that you should check this against the 3 axioms or probabilities, and you can come up with other prior distribution easily, but regardless, you should always try to make sure that it is reasonable in a sense that it does follow the 3 axioms of probability. So let me just pause here for 1 minute so you can talk to your neighbors to make sure that we all know how to check, and then justify that this choice is a reasonable choice. Okay, so the 3 axioms, first one between 0 and 1. So all of the 6 probabilities are satisfying this, right? Second is they should sum up to 1, which is true. And the third one is if you have disjoint events here, then the probability of the union of them will just be the sum of those probabilities, right? So in this case, P can be any one of this, but cannot be 2 or more than 2, right? So, and then because of that, then if we just should write, for example, that I want to know the probability of P equals to 0.3 or 0.4, then it's really just summing up 0.125 with 0.125, right? Yeah, so this is just an illustration of what that third axiom is, but U satisfies all of them for this particular probability. Make sense? All right, so again, I was saying you can come up with other prior specification easily, but you need to make sure that the prior choice is reasonable, meaning that it should satisfy the three axioms of probability. All right, so throughout the lecture, I also tried to insert appropriate R script. In this case, we're trying to use tidyverse and ggplot2. So you will see, so all of the plot, the script up there will produce the plot that I show on the screen. So when you're writing, say like working through homework or labs, maybe you can consult some of this. So in class, I wouldn't talk about why like the code will work, but you can play with things later, especially answering certain questions from homework and lab, so you can see how things can be done. But here we're trying to plot this particular prior distribution. And remember, we're saying that we have 6 different possible values. So this is a histogram here, bar plot, I should say, from 0.3 to 0.8. And we're saying that the middle two, 0.5 and 0.6, are twice as likely. Okay? So this bar graph is showing us that. All right, and so that's for the prior part. And for the data part / likelihood, let me just explain a little bit what does likelihood mean and then how we can express that. So with that prior, the Tokyo Express owner are going to give a survey, let's say to 20 customers. And let's say out of the 20 responses, 12 chose Friday. Okay. So remember, the quantity of interest is P. Okay. It's the proportion of customers prefer eating out for dinner on Friday. And it's unknown, but we're trying to make inference about it. The data or likelihood is a function of the quantity of interest. Okay, so keep in mind, later in other models, we're gonna work with likelihood as well. But regardless, it's a function of the quantity of interest, the unknown parameter. So the question here will become, what will be the function of 12 out of 20 preferring Friday in terms of the proportion? P. P is the percentage of people choosing Friday as their favorite day to eat out, right? So what will be appropriate likelihood function for this? So last time we already covered a little bit of a binomial experiment using the example of the all-nighters percentage. So we'll see that for proportion, especially when you do a survey and your interest is the unknown parameter of the proportion, then typically we're going to use the binomial likelihood function. So before we get there, let's just review binomial distribution really quick. A binomial experiment will have to satisfy 4 conditions here. So one is repeating the basic task or trial many times, and the number of total trials is n. Each trial can only be success or failure. So sorry about the extra quotes here. But regardless, it's going to be success or failure or yes or no, but there are only 2 possible outcomes for each trial. And the third condition is that the probability of a success, denoted by P, will have to be the same for each trial when you're doing a binomial experiment. And lastly, the results of each outcome will be independent. Okay, so you probably heard about the distribution Bernoulli. So Bernoulli distribution is a special case of binomial that you only do the trial once. Okay, so you have a success P, like if you flip a coin. And if it's a fair coin, P is 50%. You flip one, and that's a Bernoulli experiment. Each of them, if you keep flipping it, each of them are going to still be a Bernoulli. But if you're thinking about, well, I'm flipping 10 times, and I'm interested in the number of times that I get ahead, then that's a binomial. Okay? Each of them is Bernoulli, they're independent. But then if I care about the sum of successes, in this case, or sum of heads, then that becomes a binomial experiment. What we're doing here, with taking the survey and asking the customer's preference, Do you think it's a binomial experiment? I'm gonna pause here so you can just. So what do you all think? Do you think it's a binomial experiment? Yes or no? Anyone? Yeah, Josh?
Aiden and I talked about it, and then think it can be a binomial experiment, but under only under certain assumptions. Like if two people might be they might be friends, and one person's decision to go to the restaurant might influence the other, so that might affect the independence assumption. But if you sample the people randomly enough, I think it might it can use binomial.
Yeah, so I guess the independence assumption may be a little bit questionable here, right? Because you're just giving a survey to 20 people, and then it's possible that there people know friends in that survey. So I guess okay, but then the first two conditions are satisfied, right? We're doing a fixed number of trials, which is 20, because we're giving a survey to 20 people, so n is 20. Each trial, because we define a success in this case as choosing Friday, so it's either choosing Friday or not choosing Friday. So it is indeed a binary outcome, or only two possible outcomes. I guess number 3 and number 4 are a little bit questionable, because it's hard to determine whether all of the trials are independent. And then of course, on top of that, it's possible that people's success probability or choosing Friday might be not the same. Okay? But regardless, for simplicity, we're going to assume that we're going to do a binomial, assume this is a binomial experiment. And with that in mind, you probably have seen this before, hopefully somewhere. We need to know this density. This is, okay, so this is a discrete random variable. So we talk about PMF, okay, probability mass function. And it's talking about the probability of the random variable y takes a sequence of numbers k. So k will be between 0 and n, okay, because there are n trials in total, and k is the number of successes. So it can be 0, it can be 1, but the maximum is n. So that's why you see the range of k, and it's discrete, taking all of the integers here. And then the particular PMF, so probability mass function of a discrete random variable for the binomial will be n choose k, and then p raised to the power of k, and then 1 minus p raised to the power of n minus k. N is the number of trials, p is the number of p is the success probability, and k is for a given number, the number of successes we are able to determine the probability associated with that number. So just to, I guess, break down the PMF a little bit more, choose function n choose k is telling us how many ways we can get k successes, right, out of n trials. So that's how many scenarios you can have. And then you multiply with the probability of each scenario. So p is the success probability. And then you raise to the number of successes. And then the failure probability, 1 minus p, or raised to the power of failure n minus k. Okay? And then because there are n choose k, that's combination, n choose k, number of ways to get that, this will be the actual probability of getting exactly k successes. So this is probably a review for some of you. So keep in mind, this will be the PMF of the binomial. Okay? So last slide, I was saying that, well, the likelihood is a function of the unknown quantity of interest. Okay? So the likelihood is about the data. So now we can actually express the data in terms of the binomial PMF here. And in order to make it into a likelihood function, we're going to make sure that we can express this thing in terms of p as the only unknown. Okay. So let me bring you to that point so you know what I'm talking about. So the likelihood in this case, because we have 12 successes in 20 trials, it will be a function of the probability of success p. And typically, we're going to write what I show here in equation 5, that the unknown parameter is p in this case. And then we're trying to express the likelihood. So we use capital L to denote likelihood. And then in the parentheses, we write whatever the unknown parameter is. Okay. So this is application of the PMF that we covered, right? With the knowledge that we know small y, or k in this case, is 12. So keep in mind, in Bayesian analysis, we assume that the data is fixed. Okay, so that's why when we observe 12 successes out of 20 trials, we know that y equals to k equals to 12, and that's given. So the likelihood function is a function in terms of the unknown parameter, and the only unknown here is the p. Y or k is given as 12. So right now we are in equation 5 expressing the likelihood as a function of p. So Bayesian inference assume that the data is fixed, parameter is random. So the likelihood part of it, we always turn it into a function in terms of the parameter. And this is what we see in the binomial likelihood situation here. So generically we use L for the likelihood, it's a function of p. N is fixed, right? And known, we fixed it, it's 20. Y, even though it's a random variable, but once we observe the data, it's fixed. So it's y equals to 12 in this case. And then p is the quantity of interest. And remember earlier, before we came to the likelihood data part, we came up with one type of prior, right, for p. And then that will be the prior that we're going to work with. Now we have the likelihood. So we're going to now go to using Bayes' rule to derive the posterior distribution for the p. So keep in mind that right now the likelihood is a function of the unknown parameter p. The prior is a distribution about the unknown parameter p as well. Okay, so always focus that p is the unknown, and then everything, the prior, the likelihood, they're all functions about the unknown. Okay, and we work with this when we're trying to derive the posterior. So in order to, okay, before we go to the posterior, I just want to show you a little bit more about how you can use R and RStudio to compute the likelihood function. So this, again, we know the likelihood function in terms of the PMF is this, when y equals to 12. So obviously, in order to compute the LP, so remember, p is the only unknown parameter, right? Everything else is known. So, and we also know the p value can be 0.3 through 0.8. So essentially what we need is we need 20, which we already know, which is n here. We also need k, or small y, that's the number of successes. And once we know those two, and then plus each particular value of p, we're able to compute the likelihood function at each value. Okay? So what I want to highlight here is that you only need n, k, and the actual value of p, but the prior distribution that we used or we come up with earlier doesn't matter here. Likelihood is likelihood, prior is prior. We only use both of them together later when we're trying to derive the posterior. But then at the prior stage, make sure that you differentiate prior is prior. For the likelihood, we only need the n, the y or k, and then the values of p, but not the probabilities associated. Okay. So because a lot of stuff is going on, so sometimes everything might just feel like they're all together. But for computing the likelihood function, we don't need the prior. They are separate. So once we get clear about that, if you follow the script that I posted on the slides, you are able to use the D binorm. So remember last time when we were doing that in-class exercise, we used D binorm as well. Like I covered it really quick when we were trying to compute the binomial density for that. So binorm stands for binomial in R, and D stands for density. Okay, so this is just trying to compute that density function, and that's 20 choose 12, and then p to the power of 12, and then 1 minus p to the power of 20 minus 12. So D binorm computes that for you. Okay, you just need to fit what is the k or y, what is n, and then what is the actual probability values that you want. So once you do that, you can see that we can create one column here that is specifying the likelihood value for each of the p-value here. Okay, so this table right now, It's trying to give you a column of the values of P, the prior probability for each of the P, and then the likelihood. Okay, we need this later just because, well, we know that by Bayes' rule, we do the multiplication of the prior times the likelihood, right? And then divide it by the marginal in the end to get the posterior. So it's good to know how you can do each one of this step by step. So later on, you will see the bigger picture. Last step here is the posterior distribution. So again, just to cover a few notations, because you will see this very often throughout this course. We always use pi as, and then parentheses the unknown parameter to denote the prior distribution of the unknown parameter. In this case, is pi p. And then L is the likelihood function. And then whatever is unknown in the, as the parameter, you put it into the parentheses. And then from here, you go to pi p given y, which is, well, given the data, I'm caring about the prior or the posterior distribution of this unknown parameter. So later on, when we cover other models, you will see that we'll always keep using this notation. So you know, well, now we're dealing with prior, now we're dealing with likelihood, or now we're dealing with the posterior. The Bayes rule, we know, last time we covered it, the equation 7. This is a discrete parameter for P. So we're going to use the discrete version of the Bayes rule. That means in order to come up with the marginal probability of the data here, we will do the summation for all of the possible P values. Okay? So P pi I is the prior probability for a particular P value equals to I. LPI is that particular likelihood function at that point. And then pi pi given y will be the posterior probability at that point. Okay? The denominator gives the marginal distribution of the observation by the law of total probability, which we covered a little bit in the introduction as well. So because it's discrete, we're using summation. Later in next unit, when we're dealing with means, you will see that we're going to start using continuous distribution, and then there we'll have to do a lot of integration. All right, so how can get there? So first of all, just to show you how to use R Studio, you can compute it. So if you don't use R, I mean the rest, like computing the product and the posterior, will just be like you using a calculator, do it step by step based on Bayes rule. A lot of times you can use R and R Studio to help you get that more quickly. So remember earlier we have these 3 columns, right? We have the column of the value for P, the column of the prior distributions, and then the likelihood using the d by norm function from R. So this column, the product column, is really just taking the product of these 2 columns. Okay? So we create one more column so we get the product, and the posterior, by definition or by using Bayes' rule, we know that will be, say, the posterior for P equals to 0.3 will be that the product of that P divided by the sum of all of the product. Okay, so that's how this function we write Bayesian crank here is doing for you, but you should know the logic because it's really just following the Bayes rule like step by step. So you can get that for each of them. So the inference question for me, so you can see the probability, 6 different probabilities for each of the P values of P. So the question for you here, based on this table, is what is the posterior probability that over half of the customers prefer eating out on Friday for dinner? So a lot of times you will see that the question will be very specific to the context, right? You just have to think it through. Well, what does it mean to be over half of the customers prefer eating out on Friday for dinner based on the calculated posterior distribution that we have? I'm going to pause here. Right, so I heard, yeah, so over half will be, you add the posterior probability of 0.6 and 0.7 times, right? So essentially you're adding the probability values of this possible. Okay. Yeah, so if it's at least half, then you include the 0.5.
I think.
Right? Yeah. So you can do it by just looking at the table and then just calculate it by hand. Or in R, you know how to manipulate, you can just get that column and then add those 3 elements.
0.4.
So you can do that as well. And this is what I mean. So you can add the last 3 elements or using a logical operation here that I'm trying to sum the posterior column of my table just now, but only conditioning on the p greater than 0.5. So try out those commands if you're not familiar with R. I think those are good examples for you to go through. And it's also interesting to just like let's look at this exercise really quick. It's less than 40% in that case, so we should count or sum over all of the probabilities for p smaller or equal to 0.4, right? So just so you know, you can plot it using a particular function here is post plot, and here might not be the easiest to read, but again we plot the posterior and the prior together on the same plot, and then you can see that the prior, remember, was the middle 2 values are twice as likely as the remaining, right? And then so remember, Bayes' rule is helping us to sharpen our belief about the unknown parameter from the prior to the posterior given the data. And what was the data again? It was 12 people, right, out of 20. So the p hat, which is the sample proportion, is 0.6, right? Yeah, so, but of course, I mean, the relationship is more complicated than that, but you can see in the posterior bar plot here that this is 0.6 because the data is at 0.6, right? So it's not surprising that it's driving your inference about p to be much more likely than 0.6. You can see it from the graph, but you can also see it from the table that we saw just now. So you can do either one. But at the end of the day, I think it's always good to visualize the comparison between the prior and the posterior. Yeah, no.
So for the exercise we didn't do, the less than 40%, did you say add 0.4 and 0.3?
Yeah, so if it's less than, good question. So earlier it was, so less than 40%. Okay, so if that is the case, if it's less than 40%, then you do only 0.3.
Okay.
Yeah. And then here is mostly visualizing the prior and the posterior. And this particular function that I included here can just plot things together for you. But there are other ways through ggplot that you can do it, not like upper or like below, but also side by side. There are various ways to do this, so I encourage you to explore different ways. But in this case, I think plotting them like in this way, so you can see that all of the x-axis they match. So it's always going from 0.3 to 0.8, and then you can see how things are changing on the y-axis in terms of their probability. All right, so that's for the discrete priors. Any questions?
What package are Bayesian crank and prior post plot?
Good point. Yeah. So I didn't get to talk about it much yet, but once we get to the point that we're doing the first lab, I will cover that. But it's a package that called Prob Bayes. So later I will post a, especially once we get to lab 1. And also, I don't know if I post this. Yeah, I think I also on Moodle, in addition to the slides, I also post a R markdown file, including all of the R scripts that we use in the lecture. So at the preamble, you will see all of the packages that we loaded. But this particular package is not on-prem, it's on GitHub. So there's certain, like, I think I included the code that how you can download and install it. Yeah, so Caroline is right that prior, post, plot, and also Bayesian crank, those functions are pre-written for the purpose of teaching those material. So it's in a particular package, yeah. But other packages like public available, let's say ggplot2, you will just get it from crank directly. Yeah. Anything else? Okay. All right. If not, I will just like talk a little bit, I think.